Okay, let's begin. Yeah. So good evening, everyone, and welcome to last lecture of this doubt solving or problem solving session, right? So this is week 13, or you can consider the 13th lecture for this live interaction session, right? For this course of Matlab based programming lab in chemical engineering. Just a bit about me. I know we have been together with for this 12-week course, right? So I'm Bhavesh Moorjani. I'm a TA for this course, or I'm just ending my TA part today, right? So I have completed my bachelor's from MS University in chemical engineering, where I was introduced to this Matlab course, and then after that I was working at a production company, and then I joined IIT Bombay as a PhD. Well, I use Matlab based programming for my research work, and I that's why I took a opportunity to select this course to serve as a TA duty requirement, right? So that I can help you guys to learn MATLAB in a simpler way or in a different way. So I hope within the span of 12 week I have done justification for that aspect, and the learning journey of MATLAB was easier for you uh, based on the effort that I have put in, right? Still, if you have any doubt, or even after the course completion, if you would like to discuss something, you can contact me on my socials, right? I will try to respond you as soon as possible. Okay. So coming to the today's lecture, so this lecture we won't be learning anything new, since we have covered almost everything what has been taught in the course by sir, right? By Professor Deshpande, and we have solved various problems related to different concepts. We have understood the fundamental methodology behind it. So entire thing is covered. So this class will be more of a revision of what we have learned from week 1 till week 12. We will go through all the concepts, and then what we will do, we will discuss each of that concept, the code for different problems, what we learned, what things to considered for different examples, right? So that will be overall general idea. So it's more of a summary course, summary class, rather than any specific teaching class, right? So let's deep dive into it. So in the course, our main objective was to use MATLAB to solve various chemical engineering problems through MATLAB coding, through use of the inbuilt commands in the MATLAB, right? So here our goal was to get familiar with the MATLAB and then solve various problems in the MATLAB through programming, right? Uh, so if you remember, this is the first class concept that this is an overview of a chemical engineering process, right? So where we create a product from a raw material. So through this raw material goes through the multiple of process, be it be physical operations or chemical processes, right? Physical operation involves your all separation aspect, temperature, pressure, treatment, etc. And then chemical process or unit processes where reaction happens, and then after reaction again physical operation or unit operation you can consider, where the separation mainly takes place. So we have distillation column, we have adsorption column, right? We have different separation unit, extraction units, leaching units, etc. So depending upon what kind of materials you have, what kind of products you have, you select variety of unit operations, right? And then at the end you get a process output. Now this entire process involves multiple steps, right? Multiple things in between. So if we as a chemical engineer want to uh, design, operate or control this unit process in operation as a whole, we need to know how each of this unit works, what are the kind of models that represent these units, so that when any changes occur in the system, we can predict what will be the uh, output led by that by output led by that change in the input, right? So for that's why the concept of modeling and simulation comes, right? So when we talk about modeling, so modeling in general is a term which is referred to kind of describe your system, your physical system, in a mathematical form, right? So here what we do, so you have a physical system, physical observable. You try to create a mathematical expression which represents your system in some sort of a mathematical form, right? And once you have that model ready, you consider various scenario that is referred as a simulation. So with the help of that model, you simulate different conditions. Let's say you change various input in your model and see what will be the outcome. So that process is referred as a simulation. So these two terms, modeling and simulation, they go hand in hand together, right? So modeling is a representation of your system, and simulation is prediction of outcome, prediction of output or outcome based on that models, which go hand in hand. And when we talk about modeling and simulation, you remember I had told that time also that this aspect of modeling and simulation we do every day, right? So it's not specifically related to chemical engineering problems only. It applies to any conditions, right? uh, and model, when we say, so model can be a simplest of something like representing y equal to mx, right? So straight line curve can be also referred as model, and some complex algebraic ordinary differential equation combination can be a model also. And simulation is use of that model, right? So our day-to-day life decisions are also based on some sort of a models that we do, okay? So it doesn't have to be necessarily complex when we are talking about modeling and simulation terms, right? Now for us as a chemical engineer, when we have a process, when we have a model ready and we want to simulate it, right? So when our system is simple, our equations are simple, in that case we can solve it very nicely. Like for here, let's say if I consider physical operation of temperature change, so we have a heat exchanger for that, right? Let's say I have a heat exchanger where I want to heat my process fluid, right, from temperature uh, let's say from temperature 30 degree centigrade to 70 degree centigrade. Now I have my cold fluid also available with me. Let's say, so, sorry, we want to heat it, right, from 30 degree centigrade to 70 degree centigrade. So we have heating fluid also available, right? Let's say it's a steam at 5 bar pressure and 150 degree centigrade temperature, right? Then you can use your heat transfer equations, which is nothing but your q is equal to ua delta tlm, right, or mcp delta t, and find out what will be the change in the temperature of steam. Once you know that, once you have overall heat transfer coefficient, you can put them into ua delta tlm to find what will be the area of your heat exchanger. So that represents a simple model for your heat exchanger, right? Now when you have such simple equations in your model, you can simulate it by hand also, right? So in that case, let's say if I vary the output temperature of my process stream, let's say instead of 70 degrees centigrade I want to go to 80 degrees centigrade, while my hot fluid remains at same condition, the steam remains at the same condition, then what will be the change in the area? I can compute that easily through hand calculations, with the help of my calculator, right? If you want to reduce the temperature, instead of 70 degrees centigrade, we want to, the process requires it to be at 65 degrees centigrade. In this case, what will be the change in my heat exchanger area? Or let's say my heat exchanger area is remaining same, then what will be the output temperature of steam, right? So that sort of a thing we can compute. But when you have multiple of such equations or multiple of such models waved together, right, then in such cases your models become much complex. So for that you have to rely on some sort of a simulation techniques, right? So that's why the simulation aspect all comes into the picture. Now when we say this simulation, so there are commercial softwares already available which have this different unit processes and operations model already pre-existed, pre-coded, like our Aspen Plus. For heat exchanger you have HETRX, right? Yeah. Then you have DWSim, that's a free software similar to Aspen Plus. Uh, right? So there are multiple such softwares available. Uh, the the advantage of such software is that you don't have to change much into such software. Like you put your input parameters, software has already model present in it, and then you take out the output, right? So that's advantage of that model. But let's say when you have a very niche system, or you have some customized model for your system, in such cases we cannot rely on such simulators, right? Because your the system the equations that represent your system are not modeled in that simulator, right? So in such cases it's better to write your own code, to rely on some sort of a programming language where you code your model, and then based on your input you get the output, right? So that's the idea for the ab initio programming, right? So we learned about the ab initio programming, that what we do, we have our system models ready, we identify what kind of mathematical category they form in. So the equation that represents our system, is it a linear equation, is it a non-linear equation, is it a system of simultaneous equations, ordinary differential equation, partial differential equation, etc. Then once you know that, you try to identify what are the numerical methods to solve this to solve these equations, right? And then the final part is we implement that numerical method in the form of program in various programming language. So be C plus, Fortran, R, Python, there are various programming language available, right? And once you have that entire set ready, then you can put your user input parameters and predict the outcome, right? So here, why the important thing is the numerical method to solve the mathematical category. So as I said, that once system becomes complex, analytical solution will also become complex. So to find the solution of your problem, we have to rely on some numerical methods which simplifies and solves the problem, rather than going and finding the analytical solution, right? So if we talk about these are the various types of numerical equations that we encounter in our models, in our unit operations and unit processes, right? So your mass balance and energy balance equations for multi-component system, they are nothing but a system of simultaneous linear equations, right? So you have to solve them together to find the to solve the mass balance and energy balance problem. Then you have some non-linear equations, that to also implicit explicit equation. So reaction, when you are talking you are looking at the reaction equilibrium calculations, there you have a non-linear equations, right? Then you have ordinary differential equation, initial value problems, as well as the boundary value problems, right? So this generally are part of like ordinary differential equation. You can consider part of your reaction engineering problems also, right? So your rates are nothing but ordinary differential equation, dc by dt, with some initial condition on concentration Ca0 known. Then some diffusion problems are boundary value problems. You have coupled ordinary differential equations, then you have partial differential equations. Apart from that, we also required some of the optimization techniques in our models, to find the optimum process condition, optimum separation condition, or optimum plant operating condition, anything, okay? So such optimum conditions are required. So that's why you have to rely on some optimization process also, right? So throughout the course, what we have learned is we have looked at various problems, categorized them into this category, try to understand what are numerical methods available to solve these problems in different categories, right? And then we have coded them also. So in the coding part, what we have relied on is the Matlab programming. So Matlab, as its name says, it's a matrix laboratory, right? It's used across various engineering field, science field, too, for the data analysis part, right? The advantage of Matlab is that it has multiple numerical functions, multiple numerical methods pre-built, so within the codes of Matlab. So you don't have to kind of code this numerical methods every time. You can rely on such inbuilt packages of the MATLAB. It has a wide variety of package, and then you can solve your problems, right? So the features of MATLAB, it includes like you can do numerical computing, matrix operation, linear algebra equations. You can solve differential equations. There are optimization tools available. We can visualize data visualization, and graphics is also an important aspect. So we can plot the graphs in multiple ways, right? So although for this course, what we have seen in from this past lectures is we did not focus too much on the beautification or representation part. Okay, we mainly wanted to understand the trends, so we did not beautify the graph too much. But then again, if you want to represent your data very nicely, MATLAB has multiple such customization available in the plotting aspect also, right? Then you can write your own program, you can write your script. There are various toolbox available. You can club MATLAB with the other programming language also. So that was the aspect. Now if we look at the MATLAB, so it's a paid software, right? Right now guys have got the access through this Swayam portal, which is MATLAB online access. But apart from that, let's say if you want to work on the MATLAB, so either you have to go and buy a paid subscription, else MATLAB offers MATLAB online for free, but it has a condition. I think you can use maybe 20 to 30 hours per month MATLAB online part. So I mean, if you want to still continue your learning after the course ends, you can create your own personal account in the MATLAB online app, and then you can use it. If you have a bigger smartphone screen, then MATLAB has also mobile app already present in the Android. I'm not sure about the iOS systems, but Android has MATLAB app also. I personally used it during my BTech time to do some small assignments and stuff. So if you have a good enough screen in your phone, slightly bigger screen, you can use MATLAB to solve some of your problems also. I'm not exactly sure about the time limit that is been there in the MATLAB mobile app. As far as I know, that MATLAB online, the web page has a 20 hours per month limit. You can check it right now if they have changed it. I think MATLAB mobile does not have such limit, since it's a small screen, so you cannot fully utilize it, but still you can run a small course. So if you want to continue learning MATLAB, solve various problems in MATLAB, you can try out these things, right? So when you open the MATLAB, this is the kind of interface we get, right? So you can customize your interface by clear commands. So in this layout option, you can decide what to keep in the MATLAB, what to show in this entire window, right? What kind of layout you want to take. So the current layout that I have taken is like this, that command window is the main part, the central part. Command window is your window where you write your various commands, right? So this A is equal to 2, B is equal to, let's say, A plus 3, etc. As you are writing the command, you can see on the right hand side this workspace. Workspace includes all the variables that are being created when we are writing the commands, okay, in the command window. So this is my workspace. You can see the A and B variables are created. So it's a single variable, so 1 cross 1 is the dimension, right? If I have a matrix, so this will be like, so that's a row vector, right? 1 cross 3, 1 row 3 column kind of vector. So all the data will be displayed in the workspace. Again, it's a very useful aspect to kind of debug your code. If you are someone who has worked with C+ programming, you know that in C+ we cannot see the variables while the code is being executed, right? So you have to put some checkpoints, or you have to print out the values of your variables in between to see whether your code is working well or not. So while here in the MATLAB, as the code is being executed, your variables are created, its values are updated. You can see it in the workspace. This is again useful when you want to debug your code, right? When your code becomes complex or you are encountering some error, then you can look at the workspace. You can identify which variables are being updated, which are not being updated with respect to your loop. So that is kind of again advantage you get for the MATLAB over other conventional programming language. I know for C++ you have to print out your variables, then only you can see how they are changing the value. There are some IDEs which offer in between what it is called. Basically they temporarily save the variables and you can see them through the help of ID. But apart from that, if you run just C+ code, raw code, then you won't be able to see such variables changing, right? So that is the advantage of MATLAB. Similarly, I think in Python also you can look at the variables and see what are their values, etc., depending upon IDs that you are using. Okay, so this is the workspace. On the left hand side I have kept the folder window where we can whatever path I am in, I can see the files which are included here, right? This is the detail section. If I click on any file, it shows what that file contains, right? Then you have editor window. In editor window you can create a new script, right? For creating a new script you can use new script option. Editor window will open. We write our own code here and then save the file as .m extension, right? So .m is a MATLAB file extension, right? So whenever you see .m file, you should understand it's a MATLAB file. Apart from that, you have also the live script. So just difference between your normal script and live script is that when you are writing a normal script, so to run it you have to save it and run it, and then your output will be printed outside this scripting part. While the live script is more for a debugging option, that you are writing a code, you run it and you will be able to see what are the values or the output of your code along the side of your script itself, right? So if I put a is equal to 2, b is, let's say, 3 minus a, and I just run it, I will be able to see what will be the output alongside it, right? So it has again its own advantage in terms of debugging and understanding the various codes, right? So that is one thing. Live script has this .mlx extension. Okay, you can save this file. You can manage your file folders through various options available here. Like I can go to the other folder and select that folder. Then you can access further options based on the data provided here, right? Let's say you want to save your workspace. You have option to save your workspace, save your variables, clear the workspace. There are other plots option available. Right now we don't have much data, so it's not showing, but let's say you have plenty of data or the variables present, then such options will open up. So you can plot directly from here, or you can use the command line window also to do the plots. Then there are further add-on packages from MATLAB. So some are pre-installed, some you have to install it. So out of which we have used PD modelers, we have used optimization modelers or modules, right? The other modules, again, depending upon kind of applications you have, you can use this module with the help of this tool part, or you can also find different modules using this get more apps, design apps, packages app, etc. options, right? So let's say you found some package of the MATLAB itself which helps you to solve some specific problem. You can install it via this option, right? And then one more thing, that when you are learning any new programming language, it's nice to get familiar with the syntax of that programming language. When you do that, coding in that programming language becomes much easier for you. So it's better idea to get grasp of the basic command line options of that programming language to work faster and more efficiently. If you don't know, then you can find the help of various commands. We have seen it through time by time. Let's say if I want to do help and I want to find what does lean space mean, right? So it will, if I write help lean space, it will show me what lean space does. I can, if I click on the documentation for the lean space, we will get the separate window open, which will provide the description for the lean space command. What are the various options that I have available for that. Apart from that, you have this search documentation part, right? Where you can do, let's say I want to search about optimization and click it. It will open the Matlab documentation, search the word keyword optimization, and give you all the data, like all the possible results, keywords related to the optimization. So this is again very useful when you are searching for something, you don't know what that command used to do, right? So you can use this Matlab documentation. It's good to rely on that to get yourself updated if you forget things, right? Or you can search also, like if I want to, let's say, solve the ordinary differential equations, right? So if you just type a differential equation, it will show you all the keywords related to differential equation. So this is ordinary differential equation. It shows what are the ODEs, what are the functions we can use to solve these ODEs, right? So you can use such keywords also to find commands related to that particular topic that you are looking for. Apart from that, obviously you have currently you can use the AI tools that help you out with the various stuff. They also provide you the commands, right? But that is a secondary thing. First thing in any programming language comes is understanding the logic behind your command, right? So yeah, obviously if knowing the syntax of your command of your programming language helps you to work faster. Currently there are tools available. You can just put one search over some GPT tool and ask them to help you to code in that language, right? But the logic building is a core heart of solving your problems to programming language. And if you remember in the first class itself, I have said that when you are using that programming language to solve any problem, right? So your first focus should be over the logic building part, right? So when I say the logic building, so this is the again code to find whether the number is odd or even. That's a simple code, right? Now this is the how that code will look like over 3 different languages. So for C+, as it's a very basic fundamental language, you have to define multiple steps. It slightly looks bigger, but then the logic is same. If I want to see whether number is odd or even, what should I do? I should divide the number by 2 and see what is the remainder. If remainder is 0, that means number is even. If remainder is not 0, that means number is odd, right? So this is the basic logic behind differentiating if number is odd or even, right? So that logic remains same across all 3 languages, but just the syntax differs. So here I have this array, right? So we access element of each array. That's why the for loop comes. Then I take out that element and divide it by 2, check the remainder. If it's 0, that means number is even. If not, then number is odd. This is the logic. Same way in Python also. You access all the numbers within the array, then you divide them by 2 and find what is the remainder. If remainder is 0, that means number is even, else it's odd. Same way goes into the Matlab also. Access each component of your array, check what is the remainder of your number when you divide it by 2. If it's 0, then your number is even. If not, then your number is odd, right? So at the heart of programming language, logic building is an important aspect. So if your logics are correct, if you can form a logic nicely, you should be able to code it. Now the syntax, knowing syntax helps you uh, on creating the faster code, right? But then that thing you can solve it with the help of this AI tools also, right? But the logic building should be the core aspect when you are using any programming language. Okay, so that will be my advice to you, whether you continue programming in Matlab or you might move with the Python, which is a free package and also includes multiple of such scientific tools within it, right? So in that case also focus on the logic building, and then second thing on the knowing the syntax, so that you can work more efficiently through efficiently in that language, and solve various problems, right? So that was about the need of what is need of the programming language. So why we needed this programming language? Because we want to simulate our system with the help of various mathematical equations, which we call as a model that represents our system. So we want to do modeling and simulation together. We want to predict the outcome of our system based on the given mathematical model, right? And we know that the complexity involved in this method, solving this expression, is such that we have to rely on some software. There are commercial softwares available, but then most of them are paid. Apart from that, if they are not paid, they have less customization available. While writing on your own code, you have specific control over methods as well as various parameters that you can tune in, right? So that's why we are moving with the second route of programming. In programming, again, there are multiple options. We have selected Matlab because it's better for the numerical operations part. It's well-known programming software, right? So that's why we have started with the Matlab. So this was the gist of week 1 and week 2, right? And then we move forward with the different problems. Now when you are doing programming, this thing is left also. So when you are doing the programming, in the programming, uh, so programming language is much of a structure. Now Matlab is an interpreted language. Okay, what do you mean by the interpreted language? So it follows the program sequence by section, right? So the simplest .m file performs instruction sequentially, so one line at a time. So it will read one line, it will perform a task of that line, then move to the second line, right? However, what happens when you are doing coding of a complex system, you need not know, you need not have to go to sequences like line by line code execution. You might have to work non-sequentially, that you want some part of code to run first, then some part at the later part, right? At the later time. So for that we have a structural programming. Structural programming involves two aspects. One are decision loops, decision trees, and then seconds are loops. Okay, we have learned about use of if else conditions, right? So if else condition says that if your condition is true, then execute this part of code. If not, then execute the other part of code. So that is non-sequential code execution, right? Then that you have a for loop. For loop, you change one variable, and for each value of that variable you run a series of command within that loop. While you have while loop. So while loop works on the condition based, right? So until that condition is true, your while loop will run. Once the condition becomes false, your while loop break, right? So these are the part of this decision making structure, and the loops are the part of your structural programming that we have used to formulate our problems, right? Now what we will do is we will look at the content uh, of different weeks problem. I will touch on the gist of the idea behind that problem solving. We will look upon the code, what we did there, what things to keep in mind, and then move ahead, right? So that's the idea. That's how I have created this summary class for today's part. Just give me 1 minute. So we started with the week 3 by focusing on the what are the solution to nonlinear equations as in her system, right? So first we learned about the concept of week 3. So solution to nonlinear equation. So let's say you have any equation fx is equal to fx in the form of your values x, right? So it could be single variable, it could be multivariable, and then when we say solution to this nonlinear equation, we want to find the value of x which will correspond to fx is equal to 0, right? So for that we learned the concept of numerical methods such as bisection method, Newton-Raphson method to find the solution. So in bisection method you start with the two extremes in between where you know that there will be a there will be a x value where fx is equal to fx becomes 0, right? And then you come in between by dividing your uh, sorry by dividing your variable search half by halving your search of your variables, right? So that was the whole idea, and through that we find the solution of our equations, right? So here x square plus minus 2 times x okay sorry lower bound let's say 1, upper bound 3, accuracy 0.001. Now I have to give a bound where it will be 0. Sorry, not a good example because I have to look at the function first. Where was the function? This is week 4, right? Not week 4, week 3. Yeah, let's say so this is our equation, x to the power 4 x to the power 4 minus x minus 10. Then what are your boundaries? 1 and 2, accuracy let's say 0. And this is how you solve the problem. So you narrow down your interval a and b value based on what will be the function value that you are getting, right? And then you solve this, you do the iteration and find out what will be the value of your x. So in this case x value is 1.855, where you are getting close to the 0 value of your function, right? So so that's your solution. Okay, so for 1.8555 you are getting close to the 0 value, so that's your root. So this is how, so this is, you can see it's a non-linear equation, x to the power 4, so it's not linear, it's non-linear, and we use the bisection method to find its solution. Then similarly you have the Newton-Raphson method, which relies on the function derivative. Okay, so here also you have to enter the function, let's say this initial guess value. So I'm providing 1, accuracy again 0.01, I think I have to provide the function differently here. I forgot. Do we had a comments here? Yeah, it was in the form of x. So if I run it, x raised to 4 minus x minus 10. Yeah. What happened? Sorry, I have forgot the requirement of this code. So basically, I think we had coded it based on the providing the function inline. It's not working. Yeah, so here we had to provide the function uh, through symbols only for which the solution is needed, right? So that we did. So we have symbols x, and I have to put the function in form of the x. Yeah, that's correct. So why change the folder? x4 minus x. Okay. Maybe in the previous part we were far away from the initial point. That's why it did not give the answer. Yeah. So we are away from the initial point, so it's deviating much more. Okay. So in this problem also the initial guess becomes an important aspect, right? So that's why initial guess of 1 is not working while 2 is working. So we learned that these are the numerical methods that we can use to solve such system, right? But here also, now every time it's not wise to kind of code this bisection method, Newton-Raphson method, or any other method, right? So that's why we relied on this Matlab inbuilt solver. So for the Matlab, we have this 4 types of solvers available. you have f0, fsolve, vpa solve and solve. So every four of this command, what they does, they try to solve fx is equal to 0 with the help of various numerical methods available in that, right? But each had some different specific role. Okay, so when you have a single variable, it's wise to use f0, which finds the root of scalar nonlinear equation of single variable. If you have a multivariable function, then use fsolve command, which will solve multivariable fx is equal to 0 and provide you the multiple variable values, right? Both f0 and fsolve, you require some initial guess. Okay, and the what kind of method has been used, I have also highlighted that. Then vpa solve finds the numerical solution of symbolic equations. So here you provide the functions, but here you provide the function in the form of symbolic equation, and it gives you the numerical solutions, while solve finds the exact solution to equations. Okay, so here it provides the symbolic solution, while here it provides the numerical solution. Apart from that, you have f root also, which finds the roots of polynomial based on the, if you provide the coefficient of polynomial, right? Then when do we use this problem? Okay, so for that we looked at the example of flow through pipes, right? If you recall, we had this friction in pipe problem. So what was given in this problem was that, like, you had given the scenario, right, where you had three different pipes with different length, diameter, roughness and flow rate values, and then you were asked what will be the head loss, what will be the head loss in this pipe if I have a laminar flow and if I have a turbulent flow, and we had to compare this value provided other fluid flow conditions has been given, other process conditions were given, right? So basically what you did here was, you first list out all the input variables you have. So in this case, it's a system property: density of the fluid, viscosity of the fluid, what's the flow rate. Okay, then what are the pipe conditions? So we have created the matrix. Each row represents the pipe condition of different pipe conditions. So row 1 represents pipe 1, row 2 for pipe 2, and row 3 for pipe 3, and column represents length, diameter and E by D ratio. Then we run a loop for each pipe. So each pipe compute the compute the Reynolds number, and then we find the friction factor. Now here the friction factor in the turbulent region requires to solve this Colebrook equation, where f is at the both side, right? So we want to find the f, for which we will get the Colebrook equation as 0, okay, to find the friction factor. Okay, so that's why we rely on the f0 command, right? And once we know the friction factor, you compute the head loss, right? So that was the whole idea, and I think, yeah, this part. So it's here, sorry, my mistake. This is the only statement for the problem 1, right? So you have to use the Darcy-Weisbach equation, where you require a friction factor, and the friction factor is given by Colebrook equations, right? So that you have to find the value of f which satisfies the Colebrook equation, okay, and then you solve it through the f0 command, and find out the friction factor value and compute the head loss, right? So that was the whole idea. Let's say the second problem, where you have a laminar and turbulent region. So first you find the what is the Reynolds number, which region you are in. If you are in the laminar region, what is the friction factor, what is the head loss, and if you are in the turbulent region, then again you will have to use f0 command to find the root of your equation, right? So this was the example for flow in the pipe condition. Then we had another example for the week 4 part. So in week 4 we were solving questions related to plug flow reactor, right? So you have been given the information about the plug flow. Sorry, this is actually ordinary differential equation. I will get back to this. Yeah, this is an PFROD. Sorry, here we use ODE function. My mistake. No, I think we started with the various solvers first. again use of various solvers F0, Fsolve, etc. to find the solution of different nonlinear algebraic nonlinear equations, right? That was the idea. Then we move forward with the what are the system of linear algebraic equations, right? How they look like. So they look like this, where you have some combination of your component x1 to xn, your variable, giving you a linear equation with the coefficient varying as aij, and your right hand side of your equation represented bi, right? So this you can represent in the form of matrix ax equal to b, where your x is your unknown variables, your a is your coefficient matrix, and b is your right hand side matrix, right? So this is nothing but a system of simultaneous equation. And where do we encounter this in in chemical engineering? So mostly in the mass balance and energy balance equations. They are similar to this equation. So you have multi-component system present, then you have multiple of mass balance and energy balance equations that you have to solve together or simultaneously, right? And solution of such system of simultaneous equation relies on uh, so for that, the numerical method that we use were Gauss-Schrider, Gauss elimination method, where we coded one method also. And then there are some conditions of what kind of solution we get. So this is nothing new, but obviously you have learned it in your 11th, 12th and probably UG math course also, that what is the rank of matrix helps to determine whether we will have a unique solution for our system of equation, whether we will have infinitely many solution, no solution, etc. So when we are solving this, first thing is to check this condition. If these conditions are satisfied, let's say we are getting the unique solution, then the second aspect is to solve this problem, right? Here if we talk about Matlab, so for Matlab we have line solve, LU factorization method, inverse method, or backslash operator to find the solution of this system of linear algebraic equation, right? Where so let's see solution to Gauss elimination. So we first coded about the Gauss elimination method, a numerical method to solve system of equations. Okay. Here, not enough argument. Oh, this is function, sorry. This is again function. Infinite solution exists. Let's see if I comment this. We have unique solution, and if I use solution to Gauss elimination and A matrix, this is my answer. Just Gauss elimination and A matrix. Yeah. So the Gauss elimination function created the upper triangular matrix that we use in the this Gauss elimination part, this function, to find the solution, right? So that was the whole objective here. Okay. Now with the help of this, we solved the distillation problem. So in the distillation problem, what we had is we have been given multi-component distillation example, right? So where you have benzene, toluene, xylene, and here you had benzene, toluene, styrene and xylene separation happening in a distillation column, where we know the composition of each stream. and then we have to use mass balance to find out what is the value, what is the total value of all mass flow rates in this streams, right? The initial conditions were given, feed rates were given, okay. And we were asked, let's say if the value changes from 70 to 20 at a step interval of 5 minutes, how will be the change that you have to see, okay. So that was the whole objective. So basically here what we had first done was that first aspect is understanding the system, then second aspect is the modeling the system. So in this case, what modeling will look like, it will look like forming an mass balance equations, overall as well as the individual component mass balance equations. Once you do that, you know this is nothing but a system of simultaneous equations. So now second thing, after modeling the equation, third thing is like you have to identify what are the equations involved in your model and what are the numerical methods available to solve this problem, right? So here we know this is system of simultaneous equations, so we know Matlab has a tools to solve this system of simultaneous equation. So you know that. Then fourth aspect is code it out and find out the solution, right? So if we do that, so this was the whole code, right? So we created the A matrix, we created the B matrix, and then you have to solve your Ax equal to B, right? So here we are using lean solve function, which solves your which takes a coefficient matrix and the right hand side vector as an input and gives you the x value for Ax equal to B, right? And since it was asked like find the solution when with the step change in the feed flow rate, so this is how it will look like for different flow rates. This is how your values will change. Why did we get error in base workshop? Timer. Yeah, I don't know why that previous error came, but this is how the information will look like, right? So with the change in the input feed flow rate, what will be the change in the distillate and the bottoms of both the final columns that we have printed out, right? And this is how the trend will look like, how the trend in the change of in the feed rate will reflect on your distillate and the bottom product, right? So this is the one example. Then you can have some other example also, like leaching or the process separation part unit, which involves the physical process. So absorption becomes one, liquid extraction becomes one. Then you have a leaching process. So all this involves multi-component mass balance or overall feed balance, right? So this is nothing but your system of simultaneous equations that you have to solve together to find out the unique solution for your system. So in such cases, you have to implement this method. You have to write your system into Ax equal to B matrix form, find out the value of coefficient matrix, find out the value of your right hand side vector, and then solve the problem with the help of Matlab tools, right? So that was one aspect. After that, what we learned was solution to ordinary differential equations. Now ordinary differential equations are when you have a derivative of your function with respect to any one variable, so that becomes your ordinary differential equations, right? Now in ordinary differential equations, there are various methods to solve ODE, like your Newton-Raphson method is, or the Runge-Kutta method that we tried to code when we did the numerical method coding, are one such basics method, right? Which relies on the your fundamental numerical method to solve the what should be the solution of your f dash x equal to 0, right? So based on that only, there are various ODE functions available in Matlab, which takes your ODE function as an input, some initial guess that you have to provide, and then it will find out the solution of your problem. So if we look back, the that PFR example that we were doing for the week, we were looking in the week 4 part, or if we consider week 6, where we started with the like understanding the ordinary differential equation properly, right? So here, like what are the ODs, types of ODs also we learned, what are the stiff ODE means. Okay, so stiff ODs are where one component changes the value of your function drastically compared to other, right? So that becomes your stiff ordinary differential equations, and these were the methods out of which we did solve the Euler's method and RK method, right? And we learned about the software. So then we had looked at the unsteady state CSTR example, where both concentration and temperature. So we had two ordinary differential equation, one with respect to change in the concentration with respect to time, second change in the temperature with respect to time, and this both came from doing the mass and energy balance along the CSTR, right? And this are actually coupled. Why? Because the temperature has an effect on the rate, and rate comes in the part of your energy as well as your uh, mass balance equation, right? So it's interconnected. These are coupled ordinary differential equation, right? So like solving them analytically will become much difficult. That's why we rely on the numerical method, right? So in that numerical part, what we did was, how do I close this? Yeah, just give me a 1 or 2 minute, please. Yeah, so where were we? So we were discussing about ordinary differential equations, right? So now we have these two coupled ordinary differential equations which we have to solve simultaneously. So first, as always, like understand your system first. What are the variables in your system? We write it down, and then second is thing is to model your system. So model that is through ordinary differential equations. So we have created the function for that, which represents our system. Okay, then third thing is to identify the numerical method to solve it, which we know that for ODE we have Euler's method, Arch's method, but as of now we don't want to code the numerical method every time. So that's why we are relying on the Matlab function to solve our problems, right? So that's why we used ODE functions, right? So then we call upon the ODE. So we have used ODE 45. What is the input for your ODE 45? Your ODE equations, right? So this is your current ODE equation, the CSTR ODE. Then the time span over which you want to find out the values, right? So here we are solving the ordinary differential equations with respect to time, right? So time is our independent variable. So you have to provide the time span, let's say from t equal to 0 to let's say t equal to 20 minutes, right? So you want to solve this problem, and then initial value y0 at t equal to 0. So what we are doing here in solving an ODE is that you start with the initial point. You have ordinary differential equations, right? You know the initial condition at this point. You move ahead in a little step, right? In the step size h, if you remember, we were looking the Euler's method or Arche method, where what step size we select also becomes an important aspect, right? So you move in the step size h, you find out the value, what will be the next value of your function based on the previous data available. Then again you move ahead with the step size h, find out what should be the value based on the previous available data. So that's how you move ahead with the time or whatever independent variables you have in with respect to which ordinary differential equation is created, and find the solution by varying that values, right? So that we did, and then we find out the solution, like we displayed the solution. So this is how our plot looks like in this case. I'm sorry, I'm getting some sort of error for Matlab which should not happen. This says k is equal to 0. It should not happen. I'm not sure why it's throwing an error again. Am I having any placeholders? Continue. Let me restart it. It should not happen. This is our problem, and I'm running it. Yes, it's running fine. I don't know why previously it gave an error, right? And these are our results. So we wanted to see the variation in temperature as well as concentration with the change in the cooling water temperature or the cooling fluid temperature, right? And here the objective was whether the spike in the change in the cooling water temperature, will it affect the safety or safety of our product, will it degrade our product, right? Where we had some condition that product temperature should not be greater than 315 Kelvin for a few minutes, right? If that happens, then your product will start to degrade. So based on that you decide, like, okay, spike in temperature up to probably let's say 292 or 294 is okay. Correspondingly, what will be the change in the concentration, right? Then you also, this was the other way to plot it in, that what will be the safety limit till which you can work on the temperature aspect, right? So this was the one method to solve our ordinary differential equation. Similarly, the plug flow reactor problem that we saw in week 4, not week 4, yeah, week 4 class, yes. So you have plug PFR data, right? And you have been asked to, where it went, ODE, yeah. Solve the PFR ODE. So PFR ODE here included the change in the temperature as well as concentration, dCA by dV and dt by dV. So again, it's mass balance and energy balance combination, and we solve this problem, and this is how the output look like. That we wanted to look at the output temperature of our reactor product with the change in the input temperature and the concentration, right? So this was one objective, how the concentration will look like when you will change the CA0 and T0. Okay. So again, there are various ways to represent this data set. Here we did sensitivity analysis, etc. Again, it's fairly big problem, so since I'm not going to discuss it, we have already discussed it in greater detail. We have wrote down this code line by line in the previous class, right? So right now the gist is to recall the stuff what we did, and to remember and emphasize on what aspect to focus on, right? So mainly when we are talking about ordinary differential equation, so we have to properly represent our system in the terms of the ODE function. We have to know the initial conditions, okay, and then we can rely on this ODE solvers to find out the solution. Now here things to consider is that if your ODE is a stiff equation, right? So we saw that we have multiples option to solve this ODE, like ODE 45, ODE 15s, 23, 23s, right? So there are this 5-6 option already available. Apart from that, there might be other options also. So which option to select is a key aspect when you are dealing with multiples of such problems. Like for us as a learning purpose, we started with the ODE 45, which was giving us good results, so we stopped there. But as I said, like this ODE 15s and 23s, these are specific ordinary differential equation solvers for stiff ODE, right? So if your problem has a stiff ODE, so then you have to focus on the your differential equation that has been formed while modeling out your system also, that what kind of equations they are, what kind of nature they hold, right? If they are stiff equation, then you have to rely on the this ODE. If they are too complex, then look at the method behind this ODE solvers, right? So for example, for ODE 45 we knew that it uses explicit RK method. Now 113 uses Adams method, right? So which method works well for your model equations, right? So you have to differentiate that. Now that differentiation again obviously comes from understanding what are the numerical methods, and with experience that what kind of system requires what kind of solver. But then you have to pay attention to such aspect which as a learning objective of this course we have not focused too much on, right? But when you are solving real world problems, you have to consider that aspect also. So that is one thing to keep in mind here. Then once we solve the ordinary differential equation, we move forward with the ordinary differential equation boundary value problem. So this were the ODE IVP problems, and we had ODE BVP problems, right? Now in the boundary value problems, what we have, that you have set of equations, you have some conditions at start point, some condition at end point. Now in initial value problem, we move sequentially in the independent variable side, that we change the value of independent variable slightly, we find out what is the next value based on the previous data available. Now when you have a boundary value, you have some conditions here, conditions here, so you cannot move sequentially, and even if you move it, you have to reach out the exact value at the other boundary, right? So for that, if you want to do it manually. There is one method which is a shooting method. So in shooting method, what we do, we take a guess. So we start with the one side only, like we solve the treat the problem as initial value problem only. uh, Whatever the conditions are missing at the start point, we assume that condition, we solve the problem, we reach the end point and check whether the boundary condition that we have on the other side, is it coming same when we are solving problem as ODE IVP. If yes, then our guess is correct. If no, then based on error you refine your initial guess and work it out again, right? So that is the concept of shooting method, um, where you try to minimize the error on the boundary value by considering the problem as ODE IVP, right? So we solve the counter current heat exchanger problem, right? So where we had input at the one end, input at the other end, and then we wanted to solve this problem. So there we first utilize the shooting method to solve that problem, and then we focused on the what are the tools that we have available in the Matlab. So we learned that Matlab has a these BVP4C and BVP5C functions, which are used to solve this boundary value problem. So in that, what happens, that your entire domain is discretized. So you uh, create grids between two boundary points, and for each grids you write series of equations which represents your system, and then you solve them simultaneously, right? So that's why that's called finite difference method, and there are two main solvers available for OD boundary value problems, BVP4C and BVP5C, right? Let's look at some problems here. In week 7, no, not week 7, this is co-current. Not this one. Week 8. Yes. Right. So first, if I consider this boundary value problem as I solve this through initial value problem only, then this was the result that I was getting, right? They were fairly close, a good agreement with the what we were expecting. Why? Because obviously it's a simple problem that we had considered. Then the same problem we used the BVP4 solvers, right, in the Matlab. So you can see that part becomes much simpler here, right? Now the BVP4C, it has a specific format, right? So the format is that you have to provide the ordinary differential function first, which represents your system. You have to provide the boundary condition in the form of function, and you have to provide what is the uh, initial conditions, right? So or the initial guess value for your functions, right? So that is your BVP init part. So like again for that also, like providing the initial guess, you have BVP init function already available, where you provide the Z mesh and some initial guess, and it will create the solution init, and then entire problem is solved on its own. And same again, you will get the same sort of a plot that we got previously, right? And answers are also similar. So if you look for help, BVP4C, so this is the format or the syntax that is needed for when you use BVP4C function. You have to use create two ordinary differential function which represents your equations. Boundary conditions are also provided in the form of function, and then initial solution, right? Then this is the sample example, so you have to follow this exact format when you are using the solvers, right? And when you do that, you can call upon and find out the solutions. Okay, so further moving ahead, after working with ordinary differential equation, we come across something as partial differential equations, right? Now what is the partial differential equation? So partial differential equation comes when you have derivatives with respect to multiple variables. In ODE we had derivative of our parameters with respect to only one variable, right? Mostly time in our previous cases. But then when you have more than one variable, the derivative with respect to more than one variable, then your problem becomes partial differential equation problem, right? And it might have multiple higher order also. Now we learned about various categories, how to categorize our partial differential equations based on the this b square minus 4ac formulation, which is nothing but the coefficient for your second order derivatives with respect to your partial variables, right? So whether your function is parabolic, hyperbolic, elliptical, this is for specifically for second order PDE, right? And then we learned what are the conditions that we provide. So in partial differential equation we have boundary conditions as well as initial conditions to represent our system. Okay, so both we have to provide compared to ODE where we either will have initial conditions or only boundary conditions. But in PD you have to provide the both. And for Matlab we learn that we have this PDP solver, which is one directional partial differential equation solvers available in Matlab for a spatio-temporal problem with one space variable and one time variable, right? So your equation should follow this exact format, then only you can use PDP solver. Apart from that, for 2D geometry we can use PDE toolbox, which is graphical user interface solver, right, to solve the problem. Okay, now here if I recall the any example previously used, this is week 8, then week 9 I think, right? Yeah, heat transfer in fin. This was very good and nice example, that we have heat transfer occurring in a fin. So that fin was attached to this fin was attached to the CPU or the processor of your computer or any other device. Fin is used to provide an extended surface area for the better heat transfer, right? So what will be the change in the temperature, where heat is being generated from the base of your fin and the temperature is going in the surrounding, right? Now to solve this we had considered two approaches. One was to solve it with the help of numerical method, right? So in the numerical method what we did was, we use this finite element method. So we divided system into multiple grid points, and then for each grid points we solve the system's equations, right? And then find out what is the solution. And that we not finite element, sorry, finite difference method. So we know the from the Taylor series expansion we know the finite difference equation. We can write the first order derivative, second order derivative with respect to the difference in the function value at x plus or minus delta h, right? So that concept we utilized it and find out the values, and this is how that showed the variation in our temperature profile across the fin, right? So again, this is very interesting problem, right? I hope you guys had appreciated this problem, the kind of complexity it involved. And this is how your profile will look like at the end, right? So this was the whole idea when we were solving this heat transfer problem. Now this is the PDE example, partial differential example, but rather than using the tool, we relied on the numerical method to solve that problem, right? Now same problem, this is week 8. You can also solve with the help of some numerical solvers, right? So we had first considered the basic example of one directional film. This is PDPP solver, right? Which is for one dimensional spatio-temporal equation, partial differential equation, right? So you have one time variable and one space variable. In that cases you can use PDP solver, and again it has a very specific format that you have to create a function for your which represents your PDE function which represents your initial condition, function which represents your boundary condition. So what we learned was, if I do PDP, if I look into the documentation part for this PDP function, and this is how actually it looks like. So you have to provide the syntax, you have to follow this exact syntax, right? Where you provide first you have to kind of relate your partial differential equation with respect to this equation. You have to find out what is the value of f, what is the value of c, what is the value of m, s values, write it down. Your one function will provide CFS value, that is your PDE function. Then one function will provide initial condition, another function will provide boundary condition. Boundary condition again you have to write in the specific format of P, Q and F function, right? So you provide the lower boundary, left hand side boundary, right hand side boundary, and solve the equation. Okay, so that was the whole concept. We learned it and we implemented it. Then we move forward with the 2D problems, right, where we used PDE modeler. So in PDE modeler, so this is the kind of graphical interface we get in the PDE modeler, right, where you can draw different shapes. Okay, once you draw the shape, you have different options, like you can further build into them, do addition of your two components, subtraction between two components, right, etc. So such sort of things are possible, right? Then here edit. So here let's say you can eliminate things also. And this is how, just a minute, it's not a correct representation. Yeah, here. Now if I do this and go into PD, this is how your system looks like. If I go into draw mode, let's say my system is something like, it has a circular wedge here, the quadrupolate cut here, some centrals cut here. So this is kind of my system. So you can do such things, and then you can provide the boundary condition by going into the boundary mode. So this is how the boundary mode looks like. You can provide boundary conditions for each of this, right? So if I select show edge label, you have this many 10 boundaries. For each boundary you can provide different conditions, and here also either you can code it in a generic form, or there are some specific commonly used PDE equations modeler already available. So like for example, us as a chemical engineer, we will be focusing on the heat transfer part, right? So heat transfer part, and when you do that, and when so what it does is that it specifically changes your equation into the form that we are familiar with, right? So same PDE equation format will be changed, and it will be represented in terms of the your heat transfer parameters, your conductivity value, your heat transfer coefficient, Q values. You have to relate your expression with the expression provided here, put out the values, right? Now depending upon what kind of order you have, whether you have elliptical equation, parabolic equations, same way it will also show the boundary conditions, right? Specify boundary conditions. So whether it's a Newman boundary condition or the Dirichlet boundary conditions, right? So such information we can provide. You can create various types of complex geometries also. So what we did was we tried to see what will happen if I look at the cross sectional area of a tube of any tube of any silent tube heat exchanger, right? So that circular disc cutout example was part of that. So when you save this PD modeler file, it will create such .m file. Okay. Again, it's like a description of that GUI model, whatever we did. You can also create same GUI problem with the help of this command line option also, right? And when we run that, so this is how our system looked like, and this were the corresponding result. Like the outside had subjected to the higher temperature of 70 degrees centigrade, while inside of tube had a cold fluid which was at 30 degrees centigrade. So heat transfer will happen from the outside to inside, right? So you can see this arrow which shows the gradient change in the temperature occurring from outside to inside. This is how your temperature profile will look like in the 3 dimension, right? So again, that's an interesting aspect. Now what kind of problem you can solve here will depend upon your imagination, the kind of complexity you want to involve. Since again it's a very introductory class that we had looked for the PD modelers, so we could not go into too much complex example, and for also this was very new to me, use of this PD modeler. So I stick to the basic example so that it's much easier for me to explain and for you guys to grasp, right? But then again, you can think about what other stuff you can do, what different kind of geometry you can study, what informations you can get from such examples, right? So that was the PD modeler that we used. So this all together, the non-linear algebraic equations, linear algebraic equations, simultaneous equations, right? Ordinary differential equation, initial value problems, boundary value problems, or partial differential equations. This all stuff together somehow will kind of involve all the models that you will encounter as a chemical engineer in terms of modeling your unit operations or unit processes, right? Now the other aspect that comes is on the optimization part of this models, right? So let's say you have your model already ready, but then you have multiple conditions. But let's say in the PFR example, you have multiple of temperature conditions available, right? So in the PFR problem, when we change the value of TC to see whether the reactant temperature inside the reactor will increase to some higher value or not. So such cases, such things you can are done, like we are varying the TC value to see up to what point we can go, up to what point we can change the coolant temperature in my PFR reactor, right? So that is nothing but kind of an optimization that we are doing, that okay, maximum I can go to this point, after which my product will degrade, right? So such sort of conditioning, such sort of logic building is also required in your system, like at what condition I should operate my plant, or operate my reactor, what temperature pressure condition, so that I get the maximum yield, right? At what temperature pressure my distillation column should operate, so that I get the maximum separation, or what should be the optimum feed ratio in the case of distillation example, crude oil distillation example, that's our follows, that what should be the optimum flow rate of my fluid, the crude oil inlet feed, so that I can get the maximum profit, right? So such choices requires you to analyze the change in your output with respect to your input variable, right? So in such cases you can need that problem itself becomes an optimization problem. Now this optimization problem again involves the subcategory of this ODE, PD or non-linear or linear equations that we have studied so far, right? But they also involves us to look into the variation in the output with respect to some input variable change, right? So that becomes your optimization problem. So in optimization, what we look is we try to minimize or maximize our objective function by varying some variable, and you might be subjected to some constraints that your variable might not change uh, uh, its value beyond this point. Okay, so you might have constraint on your variable, you might have constraint on your combination of your variables, right? So such things are there, right? So what we learned was that in Matlab, to solve this problem we have multitudes of functions already available. We learned about f mean unconstrained, f mean constraint. So this both are nothing but the multivariable optimization problem. But one looks at the unconstrained problem, that where you don't have any limit um, on your decision variable, right? On the independent variable, then you have constraint where you provide the constraint. You have f mean bound, where which is a univariant optimization problem with a given boundary limit. F mean search, again it's multivariable unconstrained optimization, but it specifically uses simplex method. So the week 12, right? No, sorry, week 11 lectures that we focused on, most of the problems were looking with the help, were using this main four function. But apart from that, there are other functions also, least square non curve fitting, least square non-linear curve fitting. This is also part of optimization. You can also use least square LSQ non-linear and curve fit in terms of data fitting option also, which we learned in the last class, right? So these were the options, and what we learned was that with the help of this we can solve various optimization problems, which looks like this. Now just give me a 1 minute break. I'm sorry again. Yeah, sorry. Okay, so what is So then we had looked at couple of functions that we wanted to minimize or maximize with the help of this fmean function, fmean unconstrained, like various options that we had, right? Now for each of that we learned that they have very specific syntax. Like for example, if we consider fmean search, so here you have to provide the function value and some initial guess, and then it will work based on its own, right? When you provide same goes for the fmean unconstrained part, right? But let's say when you provide fmean constraint, so you have to provide the constraint. Now that constraint can be equality constraint, inequality constraint, right? So we look for fmean con. So this is how you have two constraints. One, your linear, which are non-equality as well as equality. Similarly, your non-linear constraint, that too non-equality and equality, right? So for your linear constraint, you have to provide the matrix value of a b, a eq, b eq. While for your non-linear constraint, you have to provide the non-linear constraint in the form of functions, right? So here some examples were also given. Same thing we do here. We provide the values of this constraint. If we have any bounds, you provide the values of bounds also, okay? And then solve these problems, right? So if we do that, this is how the we solved and compared various problems, right? So this again becomes a subcategory of problem, while your main problem itself remains on the modeling aspect, right? So but one added element is that you vary the your input parameter and find what is the optimum conditions for your output, right? So again the overall concept remains same, but then you have a added thing where you do the sensitivity analysis. Now you can do that sensitivity analysis based on your own also, like you can let's say we change the value of temperature for feed input and see how the conversion varies or how the outlet temperature varies in the PFR reactor, right? So that is kind of a sensitivity analysis, out of which if you have to find the optimum value, you put some condition and find the optimum value, or you create your entire output concentration as a function and put it into this optimizer, right? So that can also be done. So it's up to you the way you want to choose the optimization process, right? Then one more thing that we learned was on the data fitting aspect. For the data fitting, let as we have we might come across the data, the experimental data, which are at very few conditions, right? And if you want to use that data, so outside of that experimental range, experimental data set range, then you might have to do some sort of a curve fitting to extrapolate that data values apart from the experimental region also, right? So in such cases data fitting is needed. For data fitting you have so many options available in the Matlab, right? So we looked at the all options. You have polyfit and polyval. So polyfit and polyval are for the polynomial equation data fitting, right? Where polyfit fits your equation into polynomial form of n order, provides you all the coefficient value, and with the polyval you can compute the you can extrapolate the data based on your coefficient provided from the polyfit. Then you have list LSQ curve fit and LSQ non-lin. These are nothing but your least square error methods, where you change the value of your variables to minimize the error between output and the experimental data, right? Then you have spline, which uses cubical spline to fit the data. You have interp1, which interprets data based on the interpolation part. You have fit lim, fit group. Okay, so this is particularly useful for when you have multiple data sets. So you provide your data set into entire table form, and then you can relate, you can find various correlation between these data points, right? So if we reflect on some of the examples for this data fitting part, which was done on the last class, which happened to be on Friday, right? So this is how it looked like. I'm just directly running it just to show you. Right? So we found the solution. We checked the error between input and output based on the data fitting, right? And we solved various problems. So these problems were are you can find it in the week 12 class here. So we solved this various problem sets that we had some information on the experimental front, and then we tried to uh, fit a correlation between this data so that we can predict in between data points value, or we can extrapolate data set on the other conditions also, right? So this was the whole gist of your entire problem solving session, right? Now what remains is up to you to do more practice if you want to uh, make it your skill set, like enhance it your skill set in the MATLAB programming aspect, right? But apart from that, I think this whole entire 12-week course should have enabled you to use MATLAB to solve any such basic problems. Obviously, we did not touch too much complex problems also, because each of them will require more than 1 or 2 hours specifically to explain everything, to code everything, right? But this course should have helped you to gain a basic knowledge in MATLAB programming, how you can use various tools in the MATLAB to solve any problem. It doesn't have to be specifically related to chemical engineering problem. That's why some of our initial examples and the optimization and the data fitting examples are more on a common side, that you have multiples of data set and how you can utilize it, right? So it does not have to be necessary chemical engineering problems. You can solve any other engineering problems also with the help of MATLAB programming. And so I hope you have gained knowledge and have got an insight with the help with this interaction session, and I'm hope that I was able to help you or enhance your learning experience during this 12-week course, right? So that's it from my end. Now we won't have any further doubt solving session, right? I wish you best of luck for those of you who are appearing for the course certification exam, right? It was a nice journey to teach you all about this MATLAB programming, and right. So that's it. Thank you.